All too often in industrial tasks such as concrete spraying, welding, wiping, cleaning, and polishing, the operator needs to follow a particular set of motion patterns, also called skills. And the operator generally does it by means of tele operating or controlling the robot using teleoperation. So the
Okay.
setup that is generally used in such industrial tasks to solve such problems is that we have a robot that performs the action, but at the same time we have a joystick or a control arrangement that the operator handles, and the commands of the joystick or the controller are actually directly mapped to to the robot in a direct control fashion. And this is how teleoperation looks like for one of the applications where a board is being wiped. So the main idea is that the operator controls the robot via teleoperation. So to solve such problems, basically a few fundamental requirements need to be met. The robot needs to follow these specific motion patterns to achieve different goals. So these motion patterns, there could be multiple motion patterns that need to be performed sequentially to achieve, let's say, a particular goal of swiping, welding, or any of the other tasks that were mentioned before. But the main idea is that the skills should be maintained continuously and executed smoothly throughout the duration of the task, and it is very critical to the performance and to solve the task at hand. Additionally, the robot should avoid obstacles while maintaining the motions. So these are, for example, two specific skills that are being demonstrated here. So one is a wave motion pattern, and the other is a cycloid motion pattern. Uh, and there are multiple motion patterns depending on the task at hand. And at the same time, obstacle avoidance needs to be done. The obstacles could be static, that which means that the obstacles are fixed at a particular position, or they are moving. As in this case, we see that this particular ruler is being moved manually, and this is being considered as a dynamic obstacle to be avoided. So, to understand this thing more clearly, I'll take one specific example of concrete spraying for tunnel construction. And for this, the goal is actually to create a smooth concrete lining such that any waste material is avoided, and any material that collapses is also avoided. So the requirements are essentially to ensure safety of the operators when they operate close to the site, and the action that needs to be performed is a combination of two particular skills or motions, which is circular and sweeping. This is so that the rate of concrete deposition is uniform, and and a proper lining is formed for a particular task. So, for these two modes of spraying, circular and sweeping, these are the two. These are called skills or motion patterns. So now coming to the problem that is being addressed in this paper, there are a few challenges, however, with using teleoperation and for skill execution. Skill execution requires that the operators need to undergo tremendous training. Really, they need to be at expert level, and this can require months and even years to undergo such training before they can actually start teleoperating the robot. And they also cause a lot of cognitive and physical load on the operator, because a particular complicated trajectory needs to be followed in a continuous way and maintained. So these are some particular challenges in such tasks. And to avoid these challenges, or to solve and overcome these challenges, basically the ideal case scenario would be if we can automate this skill execution process such that the operator's cognitive load is totally eliminated, taking the operator out of the picture ideally. But We also want to take advantage of the operator's domain knowledge because, for example, a person who is welding for years, he knows like the specific weld patterns, the trajectories that need to be followed, and so on. So we also want to take advantage of the operator's domain knowledge, at the same time satisfying the requirements that I mentioned before, which are sustaining the skills and avoiding obstacles. So taking advantage of combining these two requirements, basically automating the task, but also taking into account the operator's domain knowledge. We actually want to assist the operator while he's performing the task, rather than completely eliminating the operator. So the idea of skill assistance or human in the loop shared control comes into picture, and this is also the primary contribution of this paper. So the idea is that the operator controls the robot by means of joystick. So the joystick controls are represented by H, and the control input is represented by U, and the state of the end effector of the robot is given by X, essentially. So, digging deeper into the idea of skill assistance, essentially, to assist the robot, we need to first understand what is the task that needs to be done, and for that, the skill needs to be identified. And before a skill is identified, we need to have a representation of the model, the movement patterns that the robot would follow. And from these movement patterns, basically, we would try to identify the skill. And once a skill is identified based on the operator's movements, then and essentially the operator's intention is recognized based on the joystick movement. We also want to adapt the motion of the robot to any changing obstacles, whether it's a boundary or a dynamic obstacle of any kind. So this is the core idea. Now I'll cover each of these individual steps in a little bit more detail. So the first step is representing the motion model. So we do this by having an underlying trajectory, which is represented by red here, and having a particular skill arrangement, which is the particular movement pattern that we talked about, like wave, cycloid, and so on. So eventually we combine this underlying trajectory and the specific skill or motion pattern to come up with a state that the robot would follow. So as we can see here that the state and theta is the parameter of the state, and it's a combination of the underlying trajectory and the skill model, essentially. And phi is the parameter for the underlying trajectory, and rho is the parameter for the skill model. We also want to control the robot. As we mentioned, the control inputs are given by u, and so we just use a velocity control model, and so the control input is just a derivative of our state. And one major contribution of this paper was that for this underlying trajectory, we are using a clothoid model, and the scales are represented such that there's a scaling factor and a rotation matrix, a scaling factor multiplied by a rotation matrix for a particular angle. So this is how the skills are represented. So combination of skills and underlying trajectory gives us the state. Now coming to the main part, which is skill identification. So skill identification is basically done by having a cost function, which is determined by the difference between our control input and the raw interface signal from the joystick. And you is the control action, as I mentioned. So this is actually now solved for different skills, and we choose the skills which offer us the smallest error. So the skills which are estimating our existing control movement, so the interface signal ideally. um, and this is how the skills are identified. If the movement of the if the raw interface signal is close to a particular skill, then that particular skill would be selected, and so on. And we also have a regularization term in this optimization, which just biases the solution towards pre-specified goals. And so digging a bit deeper into how, for example, the trajectory would be followed and how the skills would be identified. So initially, we use a direct control based arrangement, because initially we need to have some. So the prediction of future skills, we need some like timestamps for which we have signal. So initially, for some particular time duration TW, and TP here represents previous time and TC represents the current time. So for a particular time duration TW, we use direct control, and after that we use our prediction models to then predict the trajectories, and also adapt it to changing environments. So theta I and Si are the main outputs by means of which we identify skills. So skill model and the corresponding parameter description are identified. So Si and theta I essentially. And then we come to trajectory optimization. So after a skill and its parameters are identified, then we actually want to execute the trajectory for the next timestamps that closely resembles the operator's intent. So again, we use the state and the control, which are functions of our parameters. And we use again optimization subject to specific constraints. And the optimization is such that we basically minimize our theta I with estimated intention, and this way we optimize the trajectory. So combining it all together and explaining how it works. So initially we just have this experimental setup where the operator uses direct control to just use these H inputs, and basically then using inverse kinematics for the robot joint controls. We just use a direct control arrangement, but the idea of skill control to provide skill assistance to the operator comes into picture, in that now we have a switch, and after a series of after the initial phase of direct control, we can then switch to skill based shared control system, such that H is now fed into skill estimation and skill identification by means of the method that I mentioned previously. And once the skill is estimated and identified, then we want to predict the next steps, and we want to optimize the trajectory and also adapt it to the changing environments. And then we just feed it to our control inputs U, and this way we are able to assist the operator. So there's also an experimental task that is demonstrated in the paper. So for a particular task, let's say the goal is to sweep a given area of a surface, in this case this whiteboard. And the skills are there are two particular skills that are being that are required to be followed. So one is a wave like pattern, where the robot should travel in a wave back and forth along an underlying trajectory, and a cycloid pattern where it should travel in circles. So here the state x is the position of the end effector, and u is given by the 2D input planar velocity, and hr are the 2D input signals by operator via joystick. So the result of this experimental task was that This method actually demonstrates that it works for changing skill. So if a skill is being changed after a specific time instances, then these are being identified that yeah, now we are switching from, let's say, wave to cycloid, or any other pattern. It also demonstrates that for static obstacles, let's say a fixed boundary, um, the robot is able to replan the trajectory. It's able to optimize the trajectory, and likewise for dynamic obstacle avoidance.